Welcome to the AI Coach by Anil Nathu. Today we're embarking on a deep dive into the very foundations of LLMs, that's large language models. This deep dive is really all about giving you a shortcut, a way to get truly well informed on this transformative technology, getting you beyond just the headlines and into the actual mechanics.
Exactly. And we're going to really unpack the core concepts, everything from how these models are built right from the ground up to the intricate ways we guide them to behave exactly as we intend. Think of it as peeling back the layers of a magnificent machine, really, to reveal the surprising and often ingenious engineering behind this AI revolution that's happening all around us.
Absolutely.
Yeah.
Have you ever, scrolled through a perfectly coherent AI-generated story or maybe seen an LLM tackle a complex coding problem and just wondered, what actually makes this thing tick? How can it seem so intelligent, so adaptable? Well, you're about to find out.
Our mission today really is to distill the most important nuggets of knowledge from this foundational text. We want to make sure you gain a quick yet thorough understanding. We're here to equip you with the insights you need, whether you're prepping for, say, a crucial meeting, or maybe looking to catch up on this rapidly evolving field, or perhaps you're just immensely curious about what lies beneath the surface of AI.
Yeah. We'll navigate through the crucial stages of LLM development. We'll start with pre-training, that's the foundation. Then we'll move into how generative models are built, the art of prompting, the critical challenge of alignment, and finally, the efficiency of inference. And along the way, we'll offer practical guidance and key lessons, elaborating on compelling examples and case studies straight from the source material. This isn't just theory, right? It's about understanding how to effectively use, interact with, and maybe even build better AI systems. Okay, let's unpack this then. Starting with the first, truly foundational concept, pre-training. This is, in essence, the genesis, the starting point for all modern large language models. When we talk about pre-training, we're referring to that initial extensive process of optimizing a neural network before it's ever specialized for any particular task. It's like the grand general education phase for the AI.
That's a great way to put it, yeah. The core assumption here, and this is highlighted by the authors in our foundational text, is that a model pre-trained on one task can be adapted to perform another task.
Mhm.
Now, what this really means for us, for everyone, is a paradigm shift in AI development. We don't have to start from scratch every single time we want an AI to solve a new problem. This dramatically reduces the reliance on, monumental amounts of task-specific labeled data. It makes the models far more general, far more adaptable than anything we've seen before. It really democratized AI development in a significant way.
That's a profound insight. Yeah, before this, building a new AI often meant this colossal data collection effort for every single new application. So it's kind of like having a master craftsperson who understands the fundamental properties of wood, right? Allowing them to quickly adapt to build a chair or a table, maybe even a house, all from that core understanding. It dramatically lowered the barrier to creating powerful, specialized AIs. But while pre-training might feel like a new, really cutting-edge concept, our source points out that the idea actually dates back decades to the early days of deep learning.
You're right. The roots are much older than many people realize. We saw early attempts at this kind of foundational learning in things like recurrent neural networks, autoencoders, other similar architectures. But the modern era, that truly saw a resurgence, particularly with the large-scale unsupervised learning of word embeddings, things like Word2Vec, introduced by researchers like Mikolov and colleagues back in 2013 and Pennington et al. In 2014. These early models, just by learning how words relate to each other in vast amounts of text, laid really critical groundwork. Then later, models like BERT from Devlin et al. In 2019 and the original GPT by Brown et al. In 2020, they pushed this even further. They achieved what the authors describe as remarkable capability in modeling linguistic structure, all without being explicitly trained for specific linguistic tasks. So the key takeaway for you, our listener, is that pre-training establishes this broad foundation of general knowledge. It's a bit like learning the entire English language before you ever try to write a novel. It gives the model this comprehensive understanding of how language works, which it can then apply to countless situations.
Okay, so if pre-training is the bedrock, how do these models actually learn this vast general knowledge? How does it work? Our source material breaks down pre-training into three main types.
Right. The first, and probably the most historical, is unsupervised learning. This involves training on unlabeled data, essentially allowing the model to find patterns, structures, relationships within the data entirely on its own. No explicit human guidance, no corrections. While it's historically crucial for paving the way, its evolution led to more sophisticated methods, better suited for large-scale language understanding.
Then there's supervised pre-training. This is where a model is pre-trained on a specific task, but with labeled data. You can think of it like a student studying for a specific exam, maybe with all the answers already provided. Or like a system learning to classify images where every image is already tagged cat, dog, or car.
Yeah, and to give you a more detailed example from the foundations of LLMs text, imagine a sequence model designed to encode text input. This encoder is then combined with say, a classification layer. This system could be pre-trained to classify sentences based on sentiment, for instance, determining if a sentence like, "I absolutely loved that movie," conveys positive emotion, or "the service was terrible" is negative. Now, while this approach is pretty straightforward in its training, the book highlights a critical lesson for us. As the complexity of the neural network increases, the demand for more labeled data also grows. And this means it becomes incredibly difficult, almost impossible, to scale to the foundational level of LLMs without an almost unattainable amount of perfectly labeled data.
Right, the labeling bottleneck. And this is where we hit upon the true game changer, isn't it? The innovation that fundamentally altered how we approach AI training and gave us the LLMs we know today, self-supervised pre-training.
Precisely, yeah. Self-supervised learning, as defined to the authors of our foundational text, creates its own supervision signals from the input data itself. This is groundbreaking because it means the model generates its own labels directly from vast amounts of unlabeled text. It learns general linguistic structure, patterns like grammar, context, word relationships, without requiring explicit human annotation for every specific task. This approach was absolutely pivotal. It directly enabled the development of groundbreaking models like BERT and GPT, achieving that remarkable capability in modeling linguistic structure we talked about earlier. They essentially teach themselves without needing an explicit teacher for every single lesson.
So we've established self-supervised learning as the real game changer here. But how does this revolutionary idea actually work in practice? What are the ingenious tricks these models use to teach themselves from just raw, unlabeled text? Let's peel back another layer and explore the specific tasks that make it all possible. First up, masked language modeling, or MLM. It's a cornerstone for models like BERT. What's the core mechanism here?
Well, the core mechanism, as explained in Foundations of LLMs, is actually quite brilliant in its simplicity. It works by masking out some of the tokens in the input sequence and training a model to predict the masked tokens. So to give you an illustrative example, if the input sentence is "the early bird catches the worm," a mask version might become "the mask bird catches the mask." The model's job then is simply to predict the original masked words, in this case, early and worm. This task is particularly powerful because it's inherently bidirectional. That means the model uses context from both the left and the right sides of the masked word to make its prediction. This is different from simpler causal language models that only look to the left, what came before. The training objective is to maximize the reconstruction probability. Mathematically, we're trying to maximize poor x, where x is the original sequence and x is the masked version. Think of it as the model trying to prove, hey, I know it should be here, based purely on the surrounding context.
That's an incredibly clever mechanism for self-supervision. Really elegant. But like any technique this ingenious usually comes with its own unique set of quirks or limitations, right? What did researchers find were the downsides of that masking approach?
You're right. There were a couple of key challenges people ran into. One is the discrepancy caused by the MSK token itself. This special token is used only during training to represent a hidden word, but it isn't present during actual test time or inference time when you're using the model. This can create a bit of a mismatch between how the model is trained and how it's actually used later on. Additionally, the standard MLM approach can sometimes overlook the dependencies between the masked tokens. So, for instance, in our early bird worm example, the prediction of early might be made somewhat independently of worm, even though those two words are highly related and influence each other in the original sentence structure.
Ah, okay. So the mask token itself could be an issue, creating that train test gap and also overlooking dependencies between the hidden words. How did they go about solving that? This is where permuted language modeling, or PLM, entered the scene, wasn't it?
Exactly. Permuted language modeling, introduced by Yang et al. Back in 2019 with their XLNet model, was designed specifically to address these drawbacks. It involves making sequential predictions of tokens, but crucially in a permuted order, not the natural linear text sequence. Now, it's important to understand that the actual order of tokens in the original text stays the same. It's only the order in which the model is asked to predict them that changes. So, for example, if you have a sequence of 5 tokens by 0, by 1, by 2, by 3, by 4, instead of predicting them in the natural order x0, then by 1, then by 2, and so on, PLM might pick an arbitrary subsegment and predict them in a permuted order like x0 by 4, a by 2, by 1, and by 3.
Okay, so it's forcing the model to consider a wider, sort of non-sequential context for each prediction, almost like seeing around corners in the sentence.
Precisely. That's a great way to think about it. This new permuted prediction order allows tokens to be conditioned on a broader context, leveraging both left and right information, much like masked language modeling, but crucially, without using that artificial mask token. It overcomes those original limitations of MLM by effectively making the prediction of any given token dependent on other tokens that might appear later in the original sequence, but are predicted earlier in the permuted sequence. This fosters a deeper, more holistic understanding of the relationships between words. Now, for transformer architectures, this isn't implemented by explicitly reordering the tokens themselves. Rather, it's done by setting appropriate masks for self-attention within the transformer layers, as explained in our source. You can actually visualize this if you compare the self-attention masking results in Figure 1.3 of the Foundations of LLMs text. It clearly shows the difference in how causal, masked, and permuted language modeling handle context. It's quite illustrative.
Okay, so that covers models like BERT that predict within one sequence. But what about models designed for tasks that intrinsically involve, say, translating or summarizing, where there's a clear input sequence and a separate, distinct output sequence? This brings us to encoder-decoder pre-training, right?
Exactly. These architectures are fundamental for what we call sequence-to-sequence problems, such as machine translation and question answering, as our source material explains. They're explicitly built for situations where you take one sequence of information and transform it into another. One pretty straightforward approach is direct text-to-text generation. The book gives an excellent illustration. Given a text, we can ask a model to output a text describing the sentiment of the input text, such as positive, negative, and neutral.
Can you give us a more concrete example of that direct text-to-text approach, maybe with translation, something like that?
Certainly. Imagine the prompt structured like this. CLS translate from Chinese to English. O ayuasti. Hello. Mm. Here, the encoder would process the Chinese phrase, wu, and the decoder would then directly output its English translation, hello. Or, for a question answering task, CLS answer, when was Albert Einstein born? Iose, he was born on March 14th, 1879. In these cases, the encoder understands the input text, and the decoder directly generates the desired output text based on that understanding. It's a clean, direct transformation.
That's one clear way. But is there a different way these encoder-decoder models can leverage that power of self-supervision we've been discussing? Can they teach themselves in a similar way?
Yes, definitely. There's a second approach that leverages masked language modeling, but within an encoder-decoder architecture. It's similar to how BERT works.
Oh.
Tokens in the input sequence are masked. But here, the decoder is then specifically trained to predict these masked tokens. An example from the source is masking frolicking, and the in the sentence, the puppies are frolicking outside the house. The input to the encoder might be a corrupted version like CLS, the puppies are mask outside mask houser. And the decoder would be trained to output the missing pieces, maybe structured as fast frolicking bird. A fascinating variant here is denoising autoencoding. In this setup, the model maps a corrupted sequence, meaning a sequence with deliberately masked or altered tokens, to its uncorrupted counterpart. This means the model learns both deep understanding in the encoder by trying to make sense of the corrupted input and fluent generation in the decoder by producing the pristine original sequence simultaneously. It's a very powerful way to acquire broad linguistic knowledge. You can actually see a detailed illustration of this in Figure 1.4 of the Foundations of LLMs text. It really clarifies the process.
That makes sense. So the model effectively learns to fix broken sentences, essentially. Are there different, maybe more advanced ways to corrupt the input for these models to make them even more robust learners?
Absolutely. Yeah, the choice of corruption methods is really crucial and often requires extensive experimentation to find what works best for a given dataset and task. Lewis et al., in their 2020 BART model, proposed several advanced corruption methods. Beyond standard token masking, which we've already discussed, they introduced token deletion. This simply involves removing tokens from the input sequence entirely, rather than replacing them with a mask symbol. The model then has to infer not just what a word might be, but also if a word is missing and where it should go. Another really intriguing method is document rotation. Here, a token is randomly selected within a document, and the entire sequence is then rotated so that the selected token becomes the first token in the input. For instance, if you had hard work leads to success, success brings happiness, and leads was selected as the pivot, the corrupted sequence could become leads to success, success brings happiness, hard work, hard work. This forces the model to learn about the entire document structure and context in a highly nonlinear way, making it robust to variations and starting points. It's a very clever way to ensure the model builds a holistic understanding of documents, not just local phrases.
Okay, we've mentioned BERT a few times already, but that was really just a glimpse. Let's really dive into its profound impact now because it became such a true foundation model for so much that followed in NLP.
Absolutely. The authors of our source material make it crystal clear. BERT models in their various sizes like BERT base and BERT large became foundation models that can be easily adapted to different tasks via fine-tuning or prompting. They radically changed the landscape of natural language processing, often outperforming previously specialized supervised systems by a significant margin. The internal mechanism of BERT is famously based on two key self-supervised tasks: masked language modeling, MLM, which we just discussed in detail, and next sentence prediction, or NSP.
Right, NSP. And what exactly is next sentence prediction, and why was that second task so important for BERT's capabilities?
NSP, as described in Foundations of LLMs, involves taking two sentences and training the model to predict if the second one is the actual next sentence that logically follows the first in the original text. For example, the model would be given an input like, CLS, it is raining, SEP, I need an umbrella, SEP, and asked to determine if the second sentence, I need an umbrella, logically follows the first, it is raining. This isn't just about grammar, it helps BERT learn deeper semantic relationships and coherence between sentences, which is absolutely vital for many downstream tasks like question answering, summarization, and just overall document understanding. It essentially taught the model how stories and arguments flow logically.
These models sound incredibly powerful, but also incredibly resource-intensive, especially back then. What did the actual model setup and scaling look like for BERT, even in those early days?
You've hit on a key point there. Yeah, BERT models, even in their early forms, were quite large for their time and demanded significant computational resources. Their size is defined by crucial hyperparameters. There's the hidden size D, which determines the internal dimensionality of the model, the number of transformer layers, L, which is essentially how deep the model is, and the number of attention heads, N head, which dictate how many different aspects of attention the model can learn simultaneously. For instance, the original BERT-based model had a hidden size D768, L12 transformer layers, and it had 12 attention heads, totaling about 110 million parameters. BERT large was even bigger, with D1024, L24 layers, N heads, 16 heads, and a whopping 340 million parameters. Now, while these numbers might seem kind of modest compared to today's multi-trillion parameter LLMs, scaling them up even then led to significant engineering challenges. The source notes that increasing parameters often leads to unstable and difficult to converge training. It often required hundreds or even thousands of GPUs for successful and stable training. It was a real computational frontier back then.
Okay, so if these models are so powerful, but also so resource-intensive, particularly in those early days, what were the solutions? What did researchers and engineers develop to make them more efficient, both to train and maybe also to use?
Right, efficiency became a major focus. Researchers developed several ingenious techniques to improve efficiency and make these models more practical. One is knowledge distillation. This is where a smaller, more efficient student model is trained to mimic the behavior of a larger, more powerful teacher model. The smaller model learns to produce similar outputs, effectively inheriting the knowledge of the bigger one, but with fewer parameters. Another method is parameter sharing. Here, transformer layer parameters are reused across different layers or parts of the stack. Instead of each layer having its own unique set of weights, some weights are shared, significantly reducing the total number of unique parameters that need to be learned and stored. It's a clever way to get more bang for your buck, parameter-wise. Finally, dynamic networks offer a way to make inference. That's the process of actually using the model more efficient. This involves dynamically choosing which layers to activate for a given input, known as depth adaptive models, or adjusting the sequence length processed based on its importance, length adaptive models. These innovations really paved the way for more practical deployment of large models, setting the stage for the enormous LLMs we see today.
So far, we've mostly talked about models focused on a single language, usually English. But language is global, right? How do these powerful language models break through language barriers and handle a multitude of different languages effectively?
That's a truly fascinating area, and one that unlocks immense global potential. Our foundational text explains that multilingual BERT, or MBERT models, were specifically developed by training them on text from a staggering 104 different languages. The mechanism behind this is quite clever. These models use much larger vocabularies designed to cover tokens words or subword units from all these different languages. The magic happens when tokens from different languages are mapped into the same shared abstract representation space. This enables what the authors call sharing of knowledge across languages via this universal representation. It's essentially finding common ground in how different languages express similar concepts.
That sounds like it could almost learn to translate implicitly just by understanding those shared representations without being explicitly trained as a translator.
It does, yeah, to some extent. It leads to something called translation language modeling. Imagine Chinese and English sentences packed together within the training data, maybe with a subtle indicator that they're translations of each other, and then masked. For example, the model might see Ulu, Uludo, Owet, whales are mammals, and then predict masked tokens within this paired context. The book points out that predicting the Chinese token may require the information from the English token whales. This cross-lingual interaction during pre-training inherently trains the model to understand the semantic and structural correspondences between languages, even without explicit translation tasks.
And what's a practical, real-world benefit of this multilingual approach? It sounds like it could be very powerful for global communication, for instance.
A significant practical benefit of these multilingual pre-trained models is their inherent capability of handling code switching. In linguistics, code switching refers to that phenomenon of mixing languages within a single sentence or conversation, which is very common in bilingual or multilingual communities. For example, the source provides a sentence like do hiking, which expertly mixes Chinese with the English word hiking. For BERT, you don't need to identify if a token is Chinese or English. Every token is just an entry in the shared universal vocabulary. The model effectively operates in a new language that seamlessly encompasses all the languages it's trained on. This makes it incredibly versatile for understanding and generating text in diverse global contexts. It's like it learns the underlying thought, not just the surface language.
Okay, so a pre-trained BERT model is incredibly powerful, having learned this vast general understanding of language, maybe even across multiple languages. But it isn't immediately ready for a specific real-world task, right? Like classifying customer reviews accurately or answering specific medical questions. What's the next crucial step in making these models truly useful and specialized?
That next absolutely crucial step is fine-tuning. Our source material makes it clear that a pre-trained model requires additional fine-tuning work to align the output of the model with the problem of interest. The mechanism behind this is quite elegant. You integrate a small, task-specific prediction network, which we can call Predicto, with the already powerful pre-trained BERT model BERTO. The entire system, represented as Metro BERTO, is then fine-tuned on a smaller, task-specific labeled dataset. This allows the model to adapt its vast general knowledge, acquired during pre-training, to solve precise problems with high accuracy.
So it's taking that general linguistic understanding and putting it to work for a very specific job. What are some of the most common and practical applications where this fine-tuning makes a significant difference? What can we do with it?
Oh, there are many, and they cover a broad spectrum of NLP tasks. For text classification, a very common use case is classifying grammatical correctness or determining the sentiment of a piece of text. For instance, the output of BERT's special CLS token, often denoted HCLs, which represents the entire input text, is typically fed into a simple classifier. So if you input, "I love the food here, it's amazing," the model can be fine-tuned to accurately determine it has a positive sentiment. Next, there's text regression. Here, instead of assigning a category, you might predict numerical values, such as similarity scores between two pieces of text, or evaluation scores for product reviews on a scale of, say, 1 to 5. The CLS token's output could feed into a regression head that predicts a continuous value. Then we have sequence labeling, where the goal is to assign a specific label to each token in a sequence. Classic examples include part of speech, POS tagging, which identifies whether each word is a noun, verb, adjective, etc., or named entity recognition, NER. In NER, for instance, given a sentence like Tom Jenkins works at Google in New York, you'd fine-tune the model to label Tom Jenkins as BPR, beginning of person, Google as BORG, beginning of organization, and New York as BLOC, beginning of location. This allows the model to extract structured, actionable information from unstructured text. Really useful.
Those are clear examples of extracting information. What about tasks that require finding a specific part of a text in response to a question, like in reading comprehension?
Right, that falls under span prediction, which is very common in reading comprehension tasks. Here, the model is given a query and a context text, and its job is to identify a continuous segment or span within that context that best answers the query. For example, if the context is a paragraph about a historical event, and the query is, who signed the Declaration of Independence, the model would identify and output the names of the signers directly from the text. Finally, BERT models can also serve as powerful encoders for encoder-decoder models. For sequence-to-sequence tasks like machine translation or summarization, the pre-trained BERT parameters can initialize the encoder part of the system. This gives the translation or summarization system an incredibly powerful head start in understanding the source text, leveraging all that foundational knowledge before the decoder even begins generating the target sequence.
Fine-tuning sounds absolutely essential for practical applications, but it also sounds like it could potentially mess with the vast general knowledge the model gained during pre-training. Is there a common, tricky problem that arises when specializing these powerful models for new tasks? Does it forget things?
You've hit on a critical and very well-known challenge in machine learning: catastrophic forgetting. Our source notes that fine-tuning for new specific tasks may decrease its performance on the original task. This phenomenon is where a neural network, after being updated on new specific data, essentially forgets previously learned broad information or skills. It's like a specialist becoming so focused they lose sight of their general education, right? To mitigate this, common strategies include adding some of the old pre-training data back into the fine-tuning process, using more diverse data during fine-tuning, or employing specialized methods like experience replay or elastic weight consolidation, which help preserve important parameters from prior learning. Navigating these trade-offs and preserving general capabilities while specializing is complex. And this is a crucial area where resources from AI coached by Anil Nathu can really help. They can help you explore and navigate these fine-tuning strategies and avoid common pitfalls like catastrophic forgetting, ensuring your models retain their broad capabilities while specializing effectively.
Okay, we've laid the critical groundwork with pre-training, understanding how these models acquire that vast general knowledge of language. Now let's pivot to the LLMs we commonly interact with today, the truly generative models like GPT. These are the ones that have really captured the world's imagination with their ability to create coherent and creative text seemingly from scratch.
Indeed. And while LLM can broadly cover any large language model, including those like BERT that are primarily encoders, in this context, when we speak of generative LLMs, we usually refer to generative models like GPT, as our source clarifies. These models have a distinct architectural philosophy and purpose. Their main goal is to generate new original content rather than just encoding or classifying existing text.
So what's under the hood with these GPT-style models? What's the fundamental architectural design and the basic process of building them that allows them to produce such impressive creative outputs? What makes them tick?
Well, these models primarily use a decoder-only transformer architecture. Unlike BERT's bidirectional approach that considers context from both sides, these generative models generate tokens autoregressively. This means they predict the next token based entirely on all the preceding context. That includes the input prompt and all the tokens they've generated so far, one token at a time. It's like building a sentence word by word, always looking back at what's already been said to decide what comes next. The training objective for these models is essentially to maximize the log likelihood of these predictions. They learn to predict the most probable next word given everything that came before. Their core components include an input token sequence, which first gets converted into numerical representations called token and positional embeddings. These then pass through a stack of transformer blocks. These are the core computational units. Each block involves a self-attention mechanism, allowing the model to weigh the importance of different words in the input, and a feed-forward network, FFN, which further processes these weighted signals. Finally, a softmax layer produces the output distribution, which is a probability score for every possible next word in its vocabulary.
Right, and the magic within these transformer blocks often comes down to that QKV attention, query, key, and value. At a high level, it's how the model decides which parts of the input are most relevant to a specific query, dynamically assigning focus. While the deep mathematical details for QKV attention are laid out in equations 2.8 to 2.11 of the Foundations of LLMs text, the intuition is kind of like a sophisticated internal lookup and weighting system,
Right.
allowing the model to focus on the most pertinent information.
Exactly, yeah. For you, our listener, an illustrative example is maybe to think of it like a highly sophisticated autocomplete system, but on a truly massive scale. It learns to predict the most probable next word in an ongoing story or conversation based on billions, maybe trillions of examples from its training data. This allows it to generate incredibly coherent, lengthy, and contextually relevant text, making it feel like it's genuinely understanding and creating.
Okay, that explains how they generate text, word by word. But how do we get these models to do specific things beyond just continuing a text? How do we direct their immense generative power towards precise tasks, like answering specific questions or summarizing a document?
That's where instruction fine-tuning comes in, as detailed in Foundations of LLMs. We essentially define specific templates or instruction formats to guide the model. For example, if you wanted to check grammar, you might use a template like doc sentence bot question. Is this sentence grammatically correct? Answer. Then, when you input John seems happy today, question. Is this sentence grammatically correct? Answer. The model, after instruction fine-tuning, would reliably output yes. This is a powerful and flexible way to shape its behavior, making it follow explicit instructions.
And what kind of incredibly versatile applications can this instruction fine-tuning enable? It seems like these LLMs are being used for almost everything now.
Oh, the possibilities are truly vast, extending far beyond simple text completion. They can be used for story generation, responding to prompts such as, write a short story about 3 characters. Character 1, a boy whose name is Andy. Character 2, Andy's dog. Character 3, Andy's friend Jane. Well, they can also generate recipes. Show me a recipe for making ice cream. Summarize complex documents, or even tackle arithmetic problems with impressive accuracy. For example, given if you buy 5 apples and each apple costs $1.20, how much do you spend in total? A well-tuned LLM can output $6. Crucially, they can also perform code generation, responding to prompts like, write a Python program to calculate the sum of squares of the following numbers, 1, 2, 10, -9, 78. This versatility makes them incredibly powerful tools across many, many domains.
What's truly fascinating here, I think, is the idea that they can sometimes do things they weren't explicitly trained for. It's almost like an unexpected talent emerging from all that foundational learning and scale.
Absolutely. Our source notes a critical emergent ability, zero-shot learning. This means the fine-tuned models can handle new tasks that they have not been explicitly trained or fine-tuned for. This is a key differentiator from earlier, more task-specific BERT-like models. It implies that through massive pre-training, these models develop a generalized understanding of concepts and relationships that can be activated by simple, well-phrased instructions, even for tasks they've literally never encountered during training. It's almost like they've learned how to learn in a very broad sense, you know?
Right. With all this incredible power, though, to generate text, perform diverse tasks, even learn on the fly, a crucial and frankly paramount question arises. How do we make absolutely sure that LLMs are helpful, truthful, and not harmful? How do we ensure they're aligned with our human values and intentions?
This is perhaps one of the most important and complex aspects of modern LLM development. Alignment, as defined in Foundations of LLMs, is a process of guiding LLMs to behave in ways that align with human intentions. This means ensuring they are not only accurate and relevant, but also unbiased, truthful, and harmless. It's really about building AI that is helpful, harmless, and honest. Consider a stark case study highlighted in the book. If an unaligned LLM is asked how to build a weapon, it might readily provide the step-by-step instructions. However, a responsible, aligned model should recognize and avoid responding to requests for harmful or illegal information. This is directly linked to the broader field of AI safety, which aims to build safe and socially beneficial intelligence systems. It's not just about what the AI can do, but critically what it should do.
It sounds like a moving target, though.
Sure.
Human values are complex, they're diverse, they often shift over time. How do you even define something like alignment precisely enough to train a machine? That seems incredibly hard.
You're right, they are, and that's precisely the immense challenge. Human values are incredibly diverse and often shifting, making a universally precise definition difficult to pin down. Pre-training alone isn't sufficient because, as our source material points out, it is nearly impossible to gather data that encompasses all tasks or adequately represents human preferences. The raw data simply reflects the world as it is with all its biases and complexities. This necessitates specific post-pre-training alignment steps.
So what are those crucial initial alignment steps we take after the massive pre-training phase to begin instilling this crucial alignment?
Typically, 2 key approaches are adopted after the initial pre-training phase. First is supervised fine-tuning, SFT, where the model continues training on carefully curated, task-oriented, labeled data, often in the form of instruction response pairs designed to embody desired behaviors. This helps the LLM learn to follow explicit, safe commands. The second, and more advanced, is reinforcement learning from human feedback, RLHF. This is a sophisticated multi-step method that involves training a separate reward model from human preferences. This reward model then effectively guides the LLM's behavior through reinforcement learning towards outputs that humans would prefer, encompassing aspects like helpfulness, truthfulness, and harmlessness. Figure 2.2 in Foundations of LLMs provides a great overview of this intricate, multi-step RLHF process. This aspect of alignment is absolutely critical for deploying AI responsibly and ethically, and it's a core focus of the AI Coach by Anil Nathu methodology. It's about more than just raw intelligence. It's about building wisdom and ethical behavior into these powerful systems.
Right. Training these immense models, we know it isn't just about groundbreaking algorithms, it's a monumental engineering feat. It pushes the absolute boundaries of computing and infrastructure.
It absolutely is. The sheer magnitude of the challenge, as stated in Foundations of LLMs, is that it requires hundreds or thousands of GPUs to train an LLM with tens of billions of parameters from scratch. This drastically increases both the financial cost and the sheer engineering complexity of the entire development process. It's not just about having powerful hardware, but orchestrating it effectively and reliably, sometimes for weeks or even months on end.
So what kind of data do you even need for a model of this unimaginable scale? It must be enormous and incredibly diverse, right? Where does it all come from?
It is truly staggering, both in volume and breadth. LLMs are trained on massive data sets, typically ranging from zero point 0.5 to over 6 trillion tokens. To put that in perspective, if a typical book has maybe 100,000 words or tokens, we're talking about data equivalent to 5 million to 60 million books. It's immense. Table 2.3 in Foundations of LLMs details these sources. They include everything from vast collections of web pages like Common Crawl, digitized books, encyclopedic sources like Wikipedia, diverse online conversations from forums and social media, vast repositories of code, scientific and technical articles, and detailed Q&A forums. This incredibly vast and diverse data collection is precisely what enables LLMs to learn such a broad understanding of the world, language, and various forms of human expression.
But with such massive and heterogeneous data sets, I can only imagine there are significant issues and ethical considerations to contend with. Bias, privacy.
You're absolutely right. There are deeply complex challenges. One major concern is bias inherent in the training data. The source notes this isn't unique to LLMs, of course. A common example in older models might be a gender bias, where terms like nurses are disproportionately associated with women, or that specific ethnic or dialectal biases exist. While avoiding politically charged discussions is key for us here, understanding that these biases are fundamentally data-driven is important. They are often mitigated by carefully balancing categories within datasets and actively increasing language and demographic diversity in the training material. But it's a constant effort. Another critical issue, especially given the scale of public data used, is privacy. Training on extensive data sources, much of which is scraped from the internet, carries the inherent risk of exposing sensitive information. This could be intellectual property from copyrighted works or personal data that might have inadvertently been made public somewhere. Approaches to protect privacy include attempting to remove or anonymize sensitive information from the training data, though this is incredibly difficult to do perfectly at scale. Many public-facing LLMs are also subsequently fine-tuned to detect and refuse requests that could lead to privacy breaches or information leakage. These issues are complex and require constant, evolving vigilance from developers.
Okay, moving on to the model itself. Training such incredibly deep neural networks, hundreds of layers deep, can inherently be unstable, right? Making them difficult to converge reliably. How do engineers modify these complex architectures to make them trainable and robust, especially at the vast scale we're talking about?
That's a key area of architectural innovation that's often overlooked when people marvel at LLM capabilities. The Foundations of LLMs text highlights several crucial changes engineers have made. One is the strategic use of layer normalization with residual connections. For very deep transformers, a specific architectural pattern called pre-norm is widely preferred. In this setup, normalization happens before the residual connection is added back to the main path. This structure, often expressed conceptually as output L norm, F input plus input, where L norm is layer normalization and F is the main function of the layer, helps stabilize training. It does this by reducing what's called covariate shift, essentially, preventing the internal signals from wildly changing distribution as they pass through many layers. This makes the deep networks far more manageable and trainable.
So it's about keeping the internal signals stable, making sure they don't just go haywire or diminish into nothingness during such deep processing.
Exactly. Without it, gradients, those signals used to update the model, can either vanish, meaning the model just stops learning, or explode, making the training totally unstable and useless. Another critical modification involves positional embedding models. Older methods, like sinusoidal encodings, sometimes struggled with very long sequences. Many modern LLMs have moved to more advanced methods, such as rotary position embeddings or ROPE. These are designed for better handling of very long contexts, allowing models to process and understand relationships between tokens far beyond what was previously feasible. This is crucial for tasks requiring extensive context, like summarizing long documents. Beyond these architectural specifics, achieving stable and efficient large-scale LLM training also relies on a careful combination of other highly engineered aspects. Finely tuned learning schedules, how the learning rate changes over time, optimal optimizer choices, the algorithms that adjust model weights, effective parallel computation strategies, which we'll discuss next, and the widespread use of mixed precision training. These are highly engineered aspects that require extensive expertise and experimentation to get right, a testament to the sophistication involved in building these models.
Right, and no single computer, no matter how powerful, can handle the training of these massive LLMs. We're talking models with billions, even trillions, of parameters and petabytes of data. How is this immense workload split and coordinated across multiple machines, sometimes thousands, to train a single LLM?
This is where distributed training comes in, a monumental engineering challenge in itself. The core idea, as described in Foundations of LLMs, is that the training problem can be divided into smaller tasks that can be executed simultaneously across many devices, usually GPUs. There are several primary types of parallelism used to achieve this at scale. First, data parallelism. In this approach, each worker, typically a powerful GPU, runs an entire copy of the LLM model, but trains on a different subset, a mini-batch, of the total training data. After each worker computes its gradients, essentially its proposed adjustments to the model's parameters, these gradients are summed or averaged across all workers to update the model parameters. In ideal scenarios, Foundations of LLMs states that data parallelism can achieve nearly an n-fold speedup, where n is the number of workers, making it incredibly efficient for large data sets.
So it's kind of like everyone has a copy of the textbook, but they're all reading different pages simultaneously.
Yeah.
Then they all share their notes and reconcile them to update the master version. That's a great analogy.
A very apt analogy indeed, yeah. Second, there's model parallelism. This is used when an LLM is so large, its individual layers or components are so massive that it simply won't fit on a single device's memory. Here, the LLM is decoupled into components with different parts of the model, e.g. consecutive layers of the transformer stack, run on different devices. The input passes through the first group of layers on one device, then its output is passed to the next device for the next group of layers, and so on. However, this method can be less efficient because only one device is actively computing at a time in the sequential processing of layers, leading to idle time for the others. To mitigate this idle time and maximize resource utilization, tensor parallelism is often combined. This technique distributes large matrix multiplications, which are the computational heart of transformer operations, across multiple devices. Instead of putting an entire huge weight matrix on one GPU, it breaks the matrix into smaller submatrices, and each device performs a smaller part of the multiplication in parallel. This is particularly effective for maximizing the use of GPU memory and computational units simultaneously. Finally, we have pipeline parallelism. This addresses the inefficiency of basic model parallelism by dividing a batch of samples into multiple microbatches. These microbatches are then processed in a pipeline fashion. As soon as one worker finishes processing a microbatch and passes its output to the next worker in the pipeline, it immediately starts on the next microbatch. This allows different computation steps on different devices to overlap, significantly reducing idle time and improving overall throughput. The Foundations of LLMs includes clear illustrations for processing micropatches that make this concept very easy to visualize. It's quite elegant.
It sounds incredibly complex, coordinating all those moving parts across potentially thousands of GPUs.
Are there significant engineering challenges in making this all work smoothly? It can't be easy.
Oh yes, absolutely. The primary challenges in distributed training include communication overhead. That's the time and network bandwidth consumed sending data, gradients, and model updates between devices. This can become a major bottleneck, especially at huge scales. Another challenge is load imbalance, ensuring all workers are utilized efficiently and don't sit idle while waiting for others, especially with variable length inputs or complex computations. So to further boost efficiency across all these parallelism strategies, mixed precision training is widely used. This involves performing gradient computations using lower precision data types like FP16 or even FP8, while using higher precision, FP32 or FP64, for updating the model parameters. This saves memory and speeds up computation significantly, though it requires careful handling to avoid numerical issues that can sometimes arise from using lower precision.
Okay, so we've built these colossal models, orchestrated their training across thousands of GPUs, refined their architectures. But what does this all mean for how AI progresses? It seems like larger models often perform better. Is there a discernible, almost scientific pattern to this improvement? A law, perhaps?
This brings us to the fascinating and critically important concept of scaling laws, which are absolutely fundamental to understanding the trajectory and future potential of LLMs. Our foundational text defines them as relationships that describe the relationships between the performance of LLMs and the attributes of LLM training, such as the model size, the amount of computation used for training, and the amount of training data. These aren't just observations, they offer powerful predictive capabilities for AI development.
So it's not just a simple linear improvement, like double the size, double the performance. There's a specific curve or behavior that these models follow as they grow.
Precisely. Researchers like Hessness et al. Back in 2017 were among the first to show that the performance of these large neural networks often follows a power law curve. Imagine a graph where, in the beginning, performance improves slowly. Then, as more resources are added, more data, more compute, more parameters, there's a phase of rapid, almost exponential improvement. This is the crucial power law phase. Eventually, the gains typically slow down again, approaching an irreducible error that cannot be eliminated by simply scaling further. Figure 2.3 in Foundations of LLMs provides a great visual representation of these three distinct phases.
And what about these emergent abilities I keep hearing about? They sound almost magical, like a model suddenly gains a new skill it didn't have before.
That's one of the most exciting and somewhat mysterious aspects of scaling. Weigh it all. In 2022, described emergent abilities where some abilities emerge when we scale the model size to a certain level. These are skills or capabilities that are not present in smaller models but suddenly appear or become significantly better once a model reaches a certain threshold of scale. This could include complex multi-step reasoning, advanced problem solving, or even certain aspects of common sense that weren't explicitly coded or easily observable in smaller versions. It's like the pieces of a puzzle suddenly falling into place to reveal a much larger picture, something qualitatively different.
So what's the broader significance of these scaling laws for the field of AI research and development? Why do they matter so much? Why is everyone talking about them?
Their significance lies in providing directional guidance for LLM research and development. If we find we're still operating within that steep power law region, it strongly suggests that investing more resources, more data, more compute, larger models will reliably lead to better performance. This provides a clear roadmap for researchers and organizations, helping them predict how much performance gain they might achieve with increased investment and to estimate the computational resources needed to reach a desired performance level. It really guides the entire research agenda for pushing the frontier of AI capabilities.
But I assume it's not a silver bullet, right? Bigger isn't always better in every single scenario, or maybe it's not the only factor that matters.
You're astute to notice that crucial caveat. Yes, the source points out that a lower test loss does not always imply better performance on all downstream tasks. While scaling laws provide general guidance, the actual real-world performance on specific applications is also heavily influenced by subsequent steps, particularly fine-tuning and the art of prompting, which we'll explore next. It's a complex interplay of scale, training data, and how we interact with the model. These insights, like those emphasized in the AI Coach by Anil Nathur curriculum, highlight that while scale is powerful, strategic application and careful evaluation are equally vital for success.
All right, we've built, scaled, and deeply understood how these LLMs are trained, giving them incredible foundational knowledge. Now let's turn to how you, the user, actually interact with them. You've probably heard the term prompt engineering thrown around a lot lately. It's essentially the art and science of how you talk to these powerful models to get them to do exactly what you want.
That's right. Prompting, as defined in Foundations of LLMs, is simply the process of providing text inputs prompts to LLMs to elicit specific responses or behaviors. The authors also emphasize that this is one of the most notable features of LLMs. They indeed learn general knowledge about the world and language during pre-training, which we can easily apply to new challenges. The core idea here is that you're activating and reorganizing the vast knowledge that's already within the pre-trained model, all without needing to update its parameters, its weights. This enables incredibly quick adaptation to new problems and tasks, making LLMs highly versatile.
So it's like asking the right question or framing a request in just the right way to unlock the specific knowledge they already possess, rather than having to teach them something entirely new for every single task. It's transforming a complex neural network into a conversational tool.
Precisely. And this is why understanding prompt engineering is really essential for anyone using AI, from developers building applications to casual users just trying to get a good answer. It's a cornerstone of effective interaction, turning a general-purpose model into a specialized assistant for almost any task you can imagine.
Okay, so if we want to talk effectively to an LLM, what actually makes a prompt good? When you're trying to get a specific high-quality output, what are the core elements you should always consider including in your prompt?
Well, the foundations of LLMs outline several crucial general principles for effective prompt design that dramatically increase your chances of getting the desired output. These include providing a clear task description, explicitly specifying the desired output format, instructing the model to adopt a specific role or persona, and providing any necessary system information or context. For example, role-playing is incredibly powerful. You might start your prompt with something like, "You are a seasoned computer scientist with extensive knowledge in the field of deep learning. Please explain the following computer-related concept to a child around 10 years old using simple language and relatable analogies." This immediately sets the tone, the required expertise level, and the target audience for the LLM's response.
And what about that system information? How does that differ from just the main instruction or the role?
System information is a way to bake in overarching context or constraints that apply across multiple interactions, or to the LLM's general persona. A snippet like, "You are a helpful assistant and are great at grammar correction," given to the LLM helps it understand its default persona and primary objective before you even give it the specific input to correct. It sort of preconditions the model, establishing its default behavior and capabilities, which can be immensely helpful for getting consistent, reliable outputs over time.
Okay, what if a model needs a little more guidance than just instructions or a predefined role? Sometimes, seeing an example really clarifies a task for a human. Can LLMs learn from examples provided directly in the prompt itself?
They absolutely can, yeah. And this is where in-context learning, or ICL, becomes incredibly powerful. Our source material states that ICL means prompts involve demonstrations of problem solving, and LLMs can learn from these demonstrations how to solve new problems. Crucially, this happens without any parameter updates to the model itself. It's an incredibly efficient way to activate and focus the model's pre-trained knowledge on a particular pattern, style, or task format.
That's a fascinating concept, learning without actually changing its underlying brain, so to speak.
Yeah.
Can you break down how these demonstrations work, maybe from simple to more complex examples?
Certainly. We often talk about 3 levels. Zero-shot learning. This is the simplest. It involves just providing instructions without any demonstrations at all. You just tell the LLM what to do. One-shot learning. Here, you add a single demonstration to your prompt. For example, for grammar correction, you might give the LLM input. There's many reasons to celebrate. Output. There are many reasons to celebrate before presenting it with your new input for correction. It sees one correct example. Few-shot learning. This involves adding multiple demonstrations, which can be even more effective for complex tasks or nuanced patterns. For example, in mathematical reasoning, you could show it several instances like Demo 1, input 12, 5 output, 17, Demo 2, input 12, 5 output, 0.283 calculation, 12 plus 5, 12 to 5. Then you give it a new problem, and it leverages the patterns from those multiple examples.
That makes the task much clearer for the model, providing a strong template to follow. But are there any inherent limitations to this approach? Can it always learn from examples?
Yes, there's a key limitation. The effectiveness of ICL relies heavily on the quality of prompts and the fundamental abilities of pre-trained LLMs, as our source points out. So, if an LLM fundamentally lacks robust pre-training data in a specific domain or language, say a low-resource language like Inuktitut, then simply providing examples in a prompt won't magically make it proficient in translation or generation for that language. In such cases, the LLM truly lacks the underlying foundational knowledge, and no amount amount of clever prompting can fully overcome that fundamental gap. It's really about activating what's already there, not creating something entirely new from nothing.
Right, that makes sense. So beyond the basic structure and providing examples, what are some of the truly advanced moves? Those key strategies in prompt engineering that really unlock an LLM's potential and make it perform at its best, especially for complex tasks.
Our foundational text outlines several powerful strategies that go beyond the basics. First, and often overlooked but incredibly important, is providing clear and specific instructions. This goes beyond just telling it what to do. It means actively avoiding ambiguity and explicitly stating the desired output format, the length, the style, the tone, everything. For example, instead of just saying, explain climate change, you'd be far more effective with, explain the causes and effects of climate change to a 10-year-old child. Talk about how it affects the weather, sea levels, and temperatures. Also, mention some positive things people are doing to help in simple terms. And please do not exceed 500 words. This level of precision makes a huge difference in the quality and relevance of the output you get back. Second, there's the strategy of guiding LLMs to think. LLMs have shown the surprising ability to engage in more structured thought processes, especially for complex reasoning tasks. But this ability often needs to be explicitly activated. Researchers like Kojima et al. In 2022 found that simply adding a phrase like, let's think step by step, to the end of a prompt could significantly improve performance on several complex reasoning tasks. Just that simple phrase. You can even provide a detailed reasoning process within the prompt, explicitly outlining the steps you want it to follow, like step 1, understand the problem. Step 2, formulate a strategy. Step 3, perform detailed calculations. Step 4, review the solution. This forces the LLM to structure its internal processing more effectively, mimicking human problem solving. The third crucial strategy is providing reference information. This is about grounding the LLM's outputs to specific relevant text or data, preventing it from hallucinating or drawing on outdated general knowledge from its training. This is a common and powerful technique in retrieval augmented generation, or AG, where an external system fetches relevant documents first. You'd use a prompt like, you are an expert tasked with generating answers from input queries. Please generate an answer using only this context information. Paste relevant text here. This effectively confines the LLM's output, making it highly faithful to the provided facts. It's absolutely essential for ensuring accuracy and up-to-dateness, especially for factual queries.
Okay, here's where it gets really interesting. Chain of thought, or CALATA, prompting. This truly revolutionized how LLMs handle complex problems, didn't it? It was a huge step towards making their reasoning processes more transparent and, well, better.
It absolutely was, yeah. Chain of thought prompting, as our foundational text explains, involves prompting LLMs to mimic the underlying thought processes in solving the problems by explicitly generating intermediate steps or the reasoning process. Instead of just jumping to a final answer, the model actually shows its work, which is invaluable for understanding and debugging complex tasks.
Can you give us a concrete example of it showing its work that makes it so powerful? How does it look in practice?
Certainly. Let's take a classic word problem, like Tom has 12 marbles, he wins 7 more, then he loses 5. His brother gives him 3 more. How many marbles does Tom have now? If you just asked for the answer, a basic LLM might simply say 17. But with code prompting, the LLM would output something much more detailed, like, okay, let's break this down. Tom initially has 12 marbles. After winning a game, he gains 7 more, so he has 12 plus 7 equals 19 marbles. Then he loses 5 marbles the next day, bringing his total down to 19 5-liter fills. Finally, his brother gives him 3 more marbles, increasing his total to 14 plus 3 equals 17 marbles. Therefore, Tom now has 17 marbles, so the final answer is 17. This step-by-step breakdown makes the reasoning process completely explicit.
And the benefits of making that reasoning transparent are significant, I assume. It's not just about seeing the steps.
They are, tremendously. Coatney prompting has been shown to dramatically improve performance on challenging tasks, particularly in mathematical reasoning benchmarks like GSM-8K. It's also highly applicable to logical reasoning, common sense reasoning, and even generating correct and understandable code. Figure 3.1 in Foundations of LLMs showcases examples across various tasks where Coatney makes a big difference. What's even more remarkable is zero-shot SUAT, where simply adding that phrase, let's think step by step, to a prompt can induce these reasoning capabilities and significantly boost performance without any examples in the prompt itself. It hints at a deeper, more structured intelligence emerging at scale.
Okay, so for truly hard problems, sometimes even thinking step by step isn't enough. You need to break the problem down into smaller, more manageable parts first. Can LLMs do that effectively, mimicking how a human might approach a complex challenge?
They can, yeah. And it's a very effective strategy known as problem decomposition. This involves breaking an original complex problem into a series of smaller, more easily solvable subproblems, each of which can then be addressed separately, often sequentially. A notable method in this area is least to most prompting, introduced by Zhu et al. In 2023. It guides the LLM to progressively solve these subproblems in a sequential manner, building towards the final answer.
Could you give us an example of how that sequential step-by-step breakdown works in practice? How would it tackle a problem?
Certainly. Imagine you ask an LLM a question embedded in some text, like, the environmental study conducted from 2015 to 2020 revealed that the average temperature in the region increased by 2.3 degrees Celsius. What was the duration of the environmental study? Instead of trying to answer directly, least to most prompting would first decompose it. It might internally or explicitly, if prompted, ask, subprob 1Q, when did the environmental study begin? A. The environmental study began in 2015. Then, subprob 2Q, when did the environmental study end? A. The environmental study ended in 2020. Only after getting those precise sub-answers does it then pose the final question. Final Q. What was the duration of the environmental study? A. The duration of the environmental study was 5 years.
That makes so much sense. It guides the LLM through a logical progression, much like a human breaking down a math problem or a complex question.
Precisely. The immense benefit is that it tackles problems that simple few-shot learning, which just provides direct input-output examples, often cannot solve effectively. By structuring the problem into sequential, interdependent subproblems, it effectively leverages the LLM's reasoning capabilities more efficiently and accurately.
Okay, this is fascinating. Can LLMs actually learn from their own mistakes? Can they critique their own outputs and iteratively get better, much like a human reviewing their own work and revising it?
Yes, and this is a truly powerful technique called self-refinement. As detailed in Foundations of LLMs, LLMs can be prompted to critique their own outputs and iteratively refine them. It's typically a 3-step process. First, the LLM generates an initial answer to a question or prompt. Second, the same LLM is then prompted to provide constructive feedback on its own initial answer. And third, it refines the original answer based on that self-generated feedback, aiming for improvement.
That's quite sophisticated, almost a form of, well, self-awareness or self-correction. Can you walk us through a practical example of that self-correction in action? How might that look?
Imagine you ask an LLM, what are some major environmental concerns today? The LLM might first respond with a fairly general list. Major environmental concerns today include climate change, air and water pollution, deforestation, loss of biodiversity, and ocean degradation. This is accurate, but maybe a bit broad. Then, prompted for feedback on its own response, it might generate a critique like, the response provided is accurate and highlights key environmental concerns. However, it would benefit from more specific and detailed descriptions and examples. For instance, it could include specific examples of pollution sources, add information about major pollutants like greenhouse gases or plastics, and specify regions most affected by deforestation like the Amazon. Finally, given this self-generated feedback, the LLM would then refine its initial answer into something much more comprehensive and specific. Key environmental concerns include climate change, evidenced by rising global temperatures and more frequent severe weather patterns globally, significant air and water pollution, particularly in urban and industrial areas, often stemming from fossil fuel combustion and industrial waste discharge, rampant deforestation, especially in tropical regions like the Amazon rainforest, causing massive biodiversity loss, and widespread ocean degradation, highlighted by issues like coral reef bleaching due to warming waters, pervasive plastic pollution, and unsustainable overfishing practices.
That's impressive. It really shows an incredible capacity for internal critique and iterative improvement based on prompting.
It does, yeah. And it's closely related to concepts like self-reflection and self-correcting capabilities in AI. This can also be activated by prompting for more careful thinking or providing specific examples of how to critique effectively. Another example is the deliberate then generate DTG method, where LLMs are first prompted to identify specific error types in an initial output, like a translation, and then provide an improved version based on that analysis. It's all about making the LLM engage in a more thoughtful, iterative process to enhance its own outputs.
Okay, so in life, we often combine the strengths of different tools or maybe different ideas or perspectives to get a better, more robust outcome. Can we apply that same principle of combining multiple perspectives or outputs with prompts or LLM generations? Can we use ensembling for robustness?
Absolutely, and it's a very effective strategy to improve reliability and quality. Ensembling, as described in Foundations of LLMs, involves combining multiple model outputs to mitigate the impact of individual model errors and synthesize a superior final output. Each individual output might have its unique flaws, biases, or just miss certain aspects, but by intelligently combining them, you can often arrive at a more robust, accurate, and comprehensive result. It's kind of like getting multiple expert opinions on a topic and synthesizing the best parts from each.
That makes intuitive sense. What are the different ways this can be done in the context of LLMs? How do you actually ensemble these outputs?
The book outlines three main types, and you can see an excellent illustration of this in Figure 3.2 of the source material. First, model ensembling. This uses multiple different LLMs, perhaps with varying architectures or parameters, all given the same initial prompt. Their individual predictions or generations are then combined using techniques like voting for classification or averaging probabilities. Second, prompt ensembling. Here, you use a single LLM, but you feed it multiple diverse prompts for the same underlying task. Each prompt might ask the question in a slightly different way or provide different context or examples. The multiple outputs generated from these varied prompts are then combined. And third, output ensembling. This involves the LLM itself sampling multiple different outputs from its own hypothesis space. For instance, using techniques like beam search with a wider beam, or using temperature sampling to generate several candidate responses given just a single prompt. You then have a mechanism, maybe another model or a simple rule, to combine or select the best one from that pool of self-generated options.
So diversity seems absolutely key here, right? Whether it's diversity in models, prompts, or outputs, you need that variety to get a better combined result.
Yes, diversity is absolutely crucial. You want to use diverse prompts or employ sampling methods that generate a broad range of plausible responses to capture a wider spectrum of possibilities and avoid converging on a single, potentially flawed answer. Many advanced methods in this space fall under the broader category of predict then verify approaches, where an initial prediction or generation is made and then actively verified or refined, often using ensembling as part of that verification step. This adds a critical layer of scrutiny that significantly enhances the reliability and trustworthiness of LLM outputs, especially for sensitive or high-stakes applications.
Okay, so LLMs are incredibly powerful with their vast pre-trained knowledge, but as we've touched on, they don't know everything. Their knowledge base is static, frozen at the time of training, for one thing, and they certainly can't do everything, like perform precise calculations or search the current web. How do we augment their capabilities with external debate information or by giving them actions or tools they can use?
This is where retrieval augmented generation, RAG, and tool use become absolute game changers, fundamentally expanding what LLMs can achieve beyond their internal knowledge. RAG, as Foundations of LLMs explains, directly addresses LLMs' limitations regarding static or outdated knowledge by dynamically drawing from external databases and documents, much like a sophisticated real-time search engine integrated into the process. When you ask a question, relevant snippets of information are retrieved from an up-to-date knowledge source, like a database, a set of documents, or the web, and then added to the prompt, effectively augmenting the LLM's context before it generates a response.
Can you give us an example of how RAG makes an LLM immediately smarter and more current? Like, how does it work in a real query?
Certainly. If you ask an LLM, where will the 2028 Olympics be held? A RAG system would first perform a web search or maybe a lookup in a structured database related to current events. It might retrieve snippets from Wikipedia or sports news articles such as Wikipedia, the 2028 Summer Olympics, commonly known as Los Angeles 2028 or LA 28, scheduled to take place from July 14-30, 2028 in the United States. This retrieved text is then seamlessly added to the prompt given to the LLM. Only then does the LLM generate its answer, likely saying something like, based on the provided information, the 2028 Olympics will be held in Los Angeles. This ensures the model's response is factually accurate, up-to-date, and grounded in verifiable information, overcoming the limitations of its static pre-training data. And the beauty of RAG is that, in its standard form, it's largely training-free. You're just changing the input.
That's brilliant for factual accuracy in current events. But what if the retrieved information is subtly misleading, maybe irrelevant, or even completely wrong sometimes? How do we prevent the LLM from simply regurgitating bad information it's been fed by the retrieval step?
That's a very valid and critical concern, yeah. Prompts in RAG systems can be, and often are, carefully designed to make the LLM faithful to the provided facts, but also critical of them. You can even enable it to refuse to answer if the retrieved information is insufficient, contradictory, or clearly irrelevant to the user's query. For instance, if the retrieved text was only about the 2024 Olympics when asked about 2028, a well-prompted RAG model might output something like, based on the provided context which discusses the 2024 games, I don't have enough information about the 2028 Olympics. This refusal to hallucinate or make things up when the evidence isn't there is a key feature of robust RGANG implementations.
Okay, and what about tool use? How is that different from RAG, and how does it fundamentally expand what an LLM can do, not just what it knows?
Tool use is distinct from RAG because it allows LLMs to call external functions during inference, that is, during the model's active generation process, its thought process. Instead of just receiving retrieved text, the LLM can actively execute tools or APIs. For example, if you ask, where will the 2028 Olympics be held, the LLM might internally generate an action like tool.websearch query 2028 Olympics, which then triggers an actual web search via an API call. The results of that search are then provided back to the LLM for further processing and synthesizing an answer. Or for a math problem like, what is 1042? It could generate tool calculator expression 1042 to invoke a mathematical interpreter API and get the exact answer, 80, rather than trying to guess it based on its language patterns. The key distinction is that these tools are executed by the LLM during its reasoning process, not just providing pre-retrieved context. It fundamentally expands the LLM's capabilities beyond pure text generation, turning it into a more general-purpose agent that can interact with the outside world and perform actions.
Right. With all these advanced prompting techniques, from chain of thought to RAG and tool use, manually crafting the perfect prompt for every conceivable situation sounds incredibly time-consuming and, frankly, really difficult. Can we automate the creation of these effective prompts? Can LLMs, in essence, learn to prompt themselves better?
Yes, that's the exciting and rapidly evolving field of learning to prompt, and it offers several promising avenues to automate and optimize prompt creation, making it less of a manual art. One approach is prompt optimization. This essentially treats prompt engineering as a search problem, where the goal is to iteratively find the prompt that yields the best performance for a specific task. An LLM-based prompt optimization system can leverage other LLMs, or sometimes the same LLM, to evaluate candidate prompts, maintain a pool of the most promising ones based on some metric, and then generate new, refined prompts based on what's working well. It's like automated A/B testing for prompts. For example, Zhu et al. In 2023 showed how an LLM can be prompted to write a new instruction based on existing high-performing instructions, or even generate entire prompts given just input-output examples of the desired task. The significant benefit here is leveraging the LLM's own intelligence to improve its interaction and performance, effectively making it a meta-learner of prompts.
That's quite meta indeed, using LLMs to make LLMs better at understanding prompts. But what if prompts aren't even readable text to begin with? What if there's something entirely different, something the machine understands more directly?
That's where soft prompts come in. Instead of human-readable text, these are dense, low-dimensional, and learnable representations. Essentially, they are numerical vectors that directly correspond to hidden states or embeddings within the LLM. These soft prompts are optimized through continuous training, like other model parameters, rather than being crafted by a human in natural language. The benefits can be significant. They can achieve comparable performance to carefully engineered text-based prompts, but often require significantly lower computational costs for processing, especially for repeated prompts. This is because they're already in a format the model understands directly, avoiding the need for initial tokenization and embedding lookups. A prime example of this is context distillation. Here, a larger, more powerful teacher LLM, which has access to the full, complex context of a task, like a long, detailed prompt, trains a smaller, more efficient student LLM, which only sees a simplified context. The knowledge of how to respond effectively to the complex prompt is effectively distilled into the student model's parameters, which can be thought of as learning a highly effective soft prompt. This also ties into the broader field of parameter-efficient fine-tuning, PEFT, where only a small part of the model, like these prefix parameters representing the soft prompt, is optimized, making adaptation incredibly efficient in terms of compute and memory. From foundational understanding to practical application, the AI Coach by Anil Nathu platform provides resources to help you master prompting, whether you're crafting prompts manually or exploring these automated optimization techniques like soft prompts to make your models more efficient and effective.
Okay, so what does this all mean? We've built these incredibly powerful models, capable of generating text, reasoning, using tools, even learning from prompts. But power without purpose, or worse, with unintended side effects, is a profound problem, isn't it? This brings us to the absolute imperative of alignment.
This is truly where the rubber meets the road for responsible AI deployment.
Yes. LLM alignment, as defined in Foundations of LLMs, is fundamentally about aligning model outputs with human expectations. This means ensuring they're not only accurate and relevant, but also ethically sound and non-discriminatory. It's really about building AI that is helpful, harmless, and honest, reflecting the best of human values, or at least avoiding the worst.
Why is this alignment so crucial? Can't the massive pre-training, which gives them so much general knowledge from the internet and books, kind of handle it implicitly? Unfortunately, no, not reliably. Pre-trained LLMs left to their own devices might not always follow instructions accurately, might generate harmful or toxic content, or might inadvertently perpetuate biases that are present in their vast training data. They are, after all, largely reflections of the data they learn from, warts and all. The challenge is immense because, as our source points out, it is nearly impossible to gather data that encompasses all tasks or adequately represents human preferences. Human values are simply too diverse, too nuanced, and too context-dependent for pre-training alone to capture completely and reliably. Thus, alignment is a very necessary and critical post-pre-training step. While we touched on prompting earlier as a broad alignment strategy, the two primary technical approaches specifically focused on alignment are supervised fine-tuning, SFT, and the more complex reinforcement learning from human feedback, RLHF.
Okay, so if pre-training isn't enough to instill human values or ensure reliable instruction following, how do we directly teach an LLM to behave in specific ways and align with desired behaviors? Let's start with SFT.
Right. That's the primary role of supervised fine-tuning, or SFT, in the context of alignment. Foundations of LLMs explains it as continuing the training of pre-trained LLMs on new, task-oriented labeled data, specifically using carefully curated instruction-response pairs. Essentially, you show the model many examples of a given instruction, like explain this concept simply, and the desired, safe, helpful, and correct response. You're directly teaching it the preferred behavior through examples.
How does that actually work at a technical level? How do you make sure the model focuses on learning the response part, not just copying the instruction text?
The mechanism is quite clever. You can concatenate the input, the instruction, like summarize this article, and that output, the desired response, like this article discusses, into a single sequence for the model. During the training process, the loss function, the thing the model tries to minimize, is computed only for the output part during the backward pass, the learning step. This teaches the model to generate the correct response given the instruction without penalizing it for the instruction text itself. It's like telling a student, here's the question, here's the perfect answer. Now, when I give you a similar question, generate an answer just like this one. Figure 4.2 in Foundations of LLMs visually demonstrates this precise process quite well. SFT is especially vital for more complex interactions like multi-turn dialogue, ensuring coherence and safety over longer conversations. Imagine a sophisticated chatbot conversation where a user says, I've been feeling very tired lately and have a persistent headache. The LLM needs to generate context-aware, helpful, but also safe responses over multiple turns, perhaps like, I'm sorry to hear that. Persistent symptoms like that can be concerning. While I can't give medical advice, it might be a good idea to consult a healthcare professional. Have you noticed any other symptoms, like changes in sleep or diet? SFT helps it maximize the log probability of each safe and helpful response given the entire conversational history, teaching it to maintain coherence, relevance, and helpfulness throughout an extended dialogue while avoiding harmful suggestions.
What are the main challenges associated with SFT, especially considering the immense size of these models? It sounds like it could still be quite demanding, even if the data sets are smaller than pre-training.
There are two significant challenges, yeah. First, there's the sheer computational expense. Even though the fine-tuning datasets are smaller than pre-training datasets, SFT still requires significant power and memory for large models because you're still updating billions of parameters, potentially. Second, there's that recurring problem of catastrophic forgetting we discussed earlier. Overfitting to the specific SFT data can cause the model to forget some of its vast pre-trained knowledge, reducing its generalization ability or its performance on tasks not explicitly covered by the fine-tuning data. Mitigation strategies include things like regularization, early stopping, using smaller learning rates, and perhaps most importantly, fine-tuning with diverse data that includes some of its original broad knowledge or tasks to keep those capabilities alive.
How do we even get the massive amounts of labeled instruction response data needed for SFT, especially data that captures safety and helpfulness? It sounds like an enormous, expensive manual annotation effort.
It certainly can be. But innovative techniques like self-instruct, proposed by researchers like Wang et al. And Hanovich et al. In 2023, help immensely here. The idea, illustrated in Figure 4.4 of Foundations of LLMs, is remarkably clever. An LLM itself can be prompted to create new instructions, write a poem about, and then generate corresponding input-output samples, the instruction, and a safe, well-written poem. These self-generated examples are then filtered, often with some human oversight or automated checks for quality and safety, and added to a task pool, significantly reducing the manual human labeling effort required. It's kind of like the model teaching itself how to follow instructions safely by generating its own curriculum.
That's smart. So, do we always need massive SFT datasets, even with these clever generation methods? Or can small, high-quality datasets sometimes be enough?
That's a really interesting question, and there's some debate. There's a concept known as the superficial alignment hypothesis that suggests the core, broad abilities of LLMs are primarily learned during that massive pre-training phase. SFT, in this view, mainly adjusts the model's output style or teaches it to follow specific instruction formats, potentially with relatively small training fine-tuning effort. This implies that highly effective fine-tuning might be possible with smaller but very carefully selected high-quality datasets, provided the foundational pre-trained model is strong enough. However, it's worth noting that some researchers strongly argue for scaling up SFT with much larger and more diverse datasets to ensure greater robustness and broader instruction following capabilities across a wider range of nuanced tasks and safety considerations. It's an ongoing area of research how much data is truly enough for reliable alignment via SFT.
Okay, here's where we see a truly significant advancement. How do we encode those really subtle human values and nuanced preferences? Things like helpfulness, harmlessness, honesty, which are so incredibly hard to capture in simple instruction response labels. This is where reinforcement learning from human feedback, or RLHF, truly shines and has been a major breakthrough, right?
RLHF is indeed a sophisticated and incredibly powerful method, specifically designed to teach the model how to determine which outputs are more in line with human preferences. It involves a crucial two-step dance. First, training a separate reward model based on collected human preference data, which output do humans like better, and then using this reward model to guide the main LLM's refinement via reinforcement learning techniques. It's an ingenious way to transfer complex, often implicit human judgment into a quantifiable signal that an AI can understand and optimize for.
Can you walk us through that intricate RLHF process in more detail? I know Figure 2.2 and Figure 4.5 in Foundations of LLMs provide a great overview, but let's break it down.
Absolutely. It's a multi-stage process that cleverly leverages several AI techniques. It typically involves 4 key steps. 1. Initial LLM training policy. You start with an initial LLM, which is usually a powerful pre-trained model that has also undergone a phase of supervised fine-tuning, SFT. This gives you a baseline model capable of following basic instructions and generating coherent text. This LLM acts as our policy in reinforcement learning terms. It's the thing making decisions, generating text. 2, collect human preference data. This is a critical human-in-the-loop step. For a given prompt, the initial LLM generates multiple different possible responses, say 2 or 4 options. Humans are then shown these outputs and asked to rank them according to their preferences, which response is more helpful, less harmful, more truthful, better written, etc. For example, a human might indicate that response Y1 is preferred over Y4, which is preferred over Y2 and Y3. 3. Train a reward model. This ranking data is then used to train a separate, typically smaller language model called a reward model. This model's sole job is to take a prompt and a generated response and output a scalar reward score, predicting how much a human would like that response. It essentially learns to mimic human judgment. The Bradley-Terry model is often employed here, which statistically models the probability of one output being preferred over another based on their predicted reward scores. So the reward model learns human values from the ranking data. 4. RL fine-tuning, policy optimization. Finally, the original LLM, our policy model, is fine-tuned using the feedback from this trained reward model. This is framed as a reinforcement learning problem. The LLM continuously generates responses to various prompts, and the reward model evaluates them, assigning a reward score. The LLM then adjusts its parameters using RL algorithms to generate responses that maximize the reward score assigned by the reward model, thereby bringing its behavior into closer alignment with human preferences.
Okay, so how exactly does the LLM act as a policy in reinforcement learning terms? How does it make decisions about which words to generate based on this reward signal?
Right, in reinforcement learning terms. The policy, often denoted as RUS, is essentially the LLM itself. It defines the probability distribution over the next token it predicts at each step of generation. The state, S, at any given moment is the input prompt X plus all the tokens the LLM has generated so far, YT. The action A is the next token E that the LLM chooses to generate. The reward model then evaluates how good that action, or usually have a whole sequence generated, is in achieving the desired human-aligned outcome, providing that scalar reward. Value functions, VANI, are often used internally in RL algorithms to assess the expected future rewards from a given state or state action pair. Figure 4.7 in Foundations of LLMs clearly illustrates the LLM acting as a policy in this continuous feedback loop. The overarching objective is to adjust the policy, the LLM's parameters, to maximize the expected cumulative reward. This is typically achieved through policy gradient methods. And to stabilize this training process and reduce the high variance often seen in RL, techniques like using baselines, subtracting a reference point from rewards, or advantage functions, which measure how much better an action is than the average action, are commonly used, often within algorithms like A2C, advantage actor critic.
I understand a specific algorithm. Proximal policy optimization, or PPO, is particularly critical and widely used here for that RL fine-tuning step. Why PPO?
That's absolutely right. Proximal policy optimization, PPO, introduced by Schulman et al. In 2017, is indeed a popular and highly effective choice for the RL fine-tuning phase of RLHF. PPO optimizes a clipped surrogate objective function, which is a clever mathematical trick. It's designed to prevent excessively large or erratic policy updates between iterations. This helps stabilize the learning process significantly, ensuring the LLM doesn't drastically change its behavior with each update, which could make it worse, but rather learns steadily and robustly towards the human preferences encoded in the reward model. It carefully balances exploration, trying new things, and exploitation, using what the reward model indicates works well. The PPO setup for RLHF typically involves a reference model, the baseline LLM pref, often the SFT model, the target model, the LLM being actively trained, BERT, the reward model, and often a value model, which helps estimate future rewards.
And are there different nuanced ways to model those human preferences when training the reward model itself? Is it always just pick the best one?
No, there are several approaches described in our source to collect and model human preferences more effectively. Pairwise ranking, using the Bradley-Terry model, is the most common and often the most intuitive for human labelers. Humans simply indicate which of two generated outputs they prefer for a given prompt. Listwise ranking, often generalized by the Plackett-Luce model, extends this to handle scenarios where humans rank multiple items, say 4 outputs, from best to worst. This can potentially provide more signal per labeling effort. It defines a worth for each item in the list. Finally, pointwise ranking involves humans assigning absolute scores, for example 1 to 5 stars, to individual outputs. While seemingly simpler, this method can struggle with high variance and inconsistency in human feedback. My 4 stars might be your 3 stars, and might not generalize as well as comparative ranking methods which focus on relative preference. RLHF is a truly sophisticated technique, and the AI Coach by Anil Nathu platform delves deeper into the nuances of training robust reward models and applying PPO effectively. It's crucial for aligning LLMs with complex human preferences, and it's a cutting-edge field with rapid advancements constantly evolving how we instill values in AI.
Okay, RLHF is clearly incredibly powerful. But as you said, it's also complex, and not without its own set of challenges, from the cost of human feedback to the potential instabilities in RL training. How do researchers make it even better? How are they pushing beyond the basic RLHF framework to create more robust and perhaps more efficient alignment methods?
This is an area of intense and rapid research with continuous innovation happening all the time. One really significant advancement is direct preference optimization, DPO, introduced by Refalov et al. In 2024. This method radically simplifies the alignment framework by eliminating the need to explicitly model rewards. Instead of going through that multi-step process of training a separate reward model and then using complex R algorithms, DPO directly optimizes the LLM's policy based on the collected user preference pairs, which response was preferred over which.
Wow, so it effectively cuts out a whole complex step, simplifying the entire alignment process quite dramatically.
Exactly. The immense benefit is that it avoids the complexity, the computational overhead, and the potential instability associated with training and maintaining that separate reward model. DPO achieves alignment in a way that looks much more like standard, supervised learning-like fashion, making the process more straightforward, often more stable, and potentially easier to implement and scale. Figure 4.Z in Foundations of LLMs provides a clear illustrative comparison showing the architectural differences between traditional RLHF and the more streamlined DPO approach. It's a very promising direction. Another exciting innovation is automatic preference data generation. What if getting vast amounts of human feedback for RLHF or DPO is simply too slow, too expensive, or logistically challenging? The answer, increasingly, is to leverage LLMs themselves to generate preference labels, acting as AI judges. You can prompt a powerful LLM, maybe a larger, more capable one, to act as a reviewer. You give it a prompt and 2 different responses generated by the model you want to align, and ask it to indicate which response is preferred, often providing specific criteria like which response is more courteous, clear, concise, and helpful. For instance, an LLM might review two options for a customer service request and state, response A is preferred because it is more empathetic and offers clearer next steps. Variations include asking the LLM to provide a chain of thought rationale for its preference, which can then be used for process supervision, or extracting the probability the LLM assigns to each label A versus B as a confidence score.
We talked about chain of thought for complex reasoning earlier. Can we apply that same step-by-step logic, that transparency of process, directly to the alignment process itself? Aligning the process, not just the outcome.
Yes, absolutely, and this is a very promising direction known as step-by-step alignment or process supervision. Instead of just evaluating the final output of an LLM, the final answer to a math problem, this approach focuses on supervising the model during its intermediate steps of reasoning. The book distinguishes between outcome-based approaches, which only evaluate the final result, for example, is the math answer correct or not, and process-based approaches, which carefully evaluate each individual reasoning step for correctness or alignment. Consider a math problem case study from Figure 4.11 in Foundations of LLMs. One LLM response might have perfectly correct steps and a correct final answer. Another might somehow arrive at the correct final answer, but through problematic or logically flawed intermediate steps. Outcome-based alignment would treat both as equally correct, which is dangerous. But a process-based approach would meticulously catch the errors in the reasoning process of the second response. This provides more detailed supervision to LLMs by defining rewards or labels for the correctness of each individual step. This granularity leads to much more robust and trustworthy reasoning, as you're rewarding the right thinking process, not just lucky guesses.
Finally, can alignment happen during the generation process itself, at inference time, rather than just in pre-training or fine-tuning? Can we influence an LLM's behavior towards alignment as it's actually talking to a user?
Yes, that's the innovative field of inference time alignment. These are techniques designed to influence the LLM's behavior at inference time to better align with user preferences or safety guidelines without modifying the model's weights. A prime example is best of n, sampling. Here, for a given prompt, the LLM generates n different candidate outputs, maybe using temperature sampling. Then, a reward model, or even another LLM acting as a judge or simpler heuristics, selects the single best one among them based on alignment criteria, helpfulness, harmlessness, etc. This provides a simpler, more direct way to introduce human preferences or safety checks compared to full RLHF, as it directly influences the output quality during the model's actual usage phase without needing extensive iterative training cycles. This continuous evolution of alignment strategies, leveraging insights from all stages of LLM development, is really a testament to the field's rapid progress in building safer and more helpful AI systems.
Okay, we've now covered how LLMs are built, scaled, and meticulously aligned to behave responsibly. But once you have one of these incredibly powerful models, how do we actually use them efficiently? How do we get them to generate text quickly and cost-effectively in real-world applications? This is the art and engineering challenge of inference.
Right. Inference, as Foundations of LLMs defines it, is the process of generating output sequences given an input sequence. The primary goal is to efficiently search for the best output sequence given the input sequence X. Now, while that sounds straightforward, actually maximizing the probability of an output sequence, pre-YX, is incredibly computationally intensive. The number of possible output sequences grows exponentially with the length of Y, making an exhaustive search checking every possible word combination utterly impractical for LLMs. You'd never get an answer.
So it's about smart shortcuts and incredibly efficient computation, finding a good enough answer very quickly rather than a theoretically perfect answer that would take forever.
Exactly. The key focus is on two things: efficiently computing pre-AIX, that is, the probability of generating specific outputs, and devising efficient, albeit often suboptimal, search strategies for finding a high probability. What's particularly exciting and a relatively new approach is the emerging field of inference timescaling. Our source notes that injecting additional prompts and contextual information, such as long chain of thought prompts, during inference can significantly improve the performance of LLMs. This provides a powerful new approach to scaling LLMs, exemplified by advanced systems like OpenAI's O1 and DeepSeek's R1. These systems demonstrate impressive performance on complex reasoning by intelligently increasing computation at the time of inference, not just during initial training. Understanding inference optimization is absolutely critical for real-world deployment of AI, directly impacting speed, cost, and ultimately the user experience. This focus on practical application and efficiency is a cornerstone of the AI coach by Anil Nathu methodology.
Okay, how does an LLM actually start processing your input prompt and then continue generating its response, token by token? It's not just one monolithic process, is it? It's actually a distinct two-stage framework.
That's right. The Foundations of LLMs describes this as a two-phase framework that optimizes the whole process for efficiency. The first phase is prefilling. This is where the LLM processes the entire input sequence, your prompt, all at once. The goal here isn't to generate output yet, but to build a context representation, specifically the KV cache, key value cache, which stores internal states for all the subsequent generation steps. Think of it like the LLM quickly reading and understanding your full prompt first, absorbing all its nuances and preparing its internal state, its memory, to respond coherently. Prefilling is typically compute-bound, meaning its performance bottleneck comes from the raw computational capacity of the GPU, and it can be highly parallelized, processing all input tokens simultaneously using the attention mechanism.
And then once it's fully understood the prompt and built that internal context, that KV cache, it starts talking right word by word.
Precisely. That leads to the second phase, decoding.
Right.
This is where the LLM generates the output sequence, token by token, auto-regressively predicting each next token Y based on the initial input X and all the previous output tokens it has already generated. This phase is typically memory-bound, meaning the bottleneck often comes from memory bandwidth, the speed at which data, especially that growing KV cache, can be moved to and from the GPU's memory. And it's performed sequentially, one token after another, because each token depends on the previous one. The crucial element here is the KV cache that was built during prefilling. It stores past activations, the keys and values from the attention layers, for all the input tokens and previously generated tokens. This prevents the model from having to wastefully recompute them for every single new token it generates. Although, as you noted, its size grows linearly with the sequence length, which can become a memory challenge for very long outputs. Figure 5.3 in Foundations of LLMs provides a clear illustration of this prefilling and decoding dynamic in action.
Okay, so during that decoding phase, with so many possible words at each step, literally tens of thousands of options in the vocabulary, how does an LLM choose the best next word? It sounds like a massive and incredibly complex search problem through all possible sentences.
It absolutely is a search problem, yeah. It's often visualized as navigating a search tree, much like the one illustrated in Figure 5.4 in Foundations of LLMs. Each node in this tree represents a partial sequence or prefix that the LLM has generated so far. Branches extend out from each node to all possible next tokens, words in the vocabulary. The ultimate goal is to find the path through this exponentially large tree that yields the highest overall probability for the entire output sequence, representing the most coherent and likely generation according to the model.
What's the simplest, most straightforward way to pick the next word in that search tree? Just grab the best one.
The simplest method is greedy decoding. As our source material explains, at each step, the model simply selects the single token that has the absolute highest probability from its prediction distribution for that step. It's the most computationally efficient and straightforward approach. The benefit is speed and simplicity. It makes an immediate, confident choice. However, its primary drawback is its suboptimal nature. High-quality sequences are likely pruned at early stages. It can easily get stuck in local optima, meaning it might choose a word that looks best right now but prevents it from finding a globally better, more coherent, or more creative sequence later on. It doesn't look ahead at all.
Okay, so greedy is fast, but maybe not the best quality. How do we balance that desire for efficiency with the need to find better, higher quality outputs that greedy decoding might miss?
That's where beam search comes in. Instead of just following the single best path, it maintains a beam of k most promising partial sequences at each step. It works like this. It expands each of these k sequences by considering all possible next tokens, calculates the probabilities of these expanded sequences, and then prunes the expanded set back down, keeping only the top k most probable candidates overall. These k candidates then become the starting points for the next step. This significantly improves search quality over greedy decoding without resorting to a computationally impossible exhaustive search. The beam with k is a crucial parameter. It balances efficiency and accuracy. Often, a relatively small value like K2 or K4 is sufficient to get a substantial quality improvement over greedy.
Right. What if we want more creative, diverse, or less predictable outputs, though? Not just the single most probable sequence or even the top K. This is often key for tasks like story generation or brainstorming.
Exactly. For creativity and diversity, we turn to sampling-based decoding methods, which introduce an element of controlled randomness into the process. The most basic is basic sampling, where the next token is simply sampled probabilistically from the predicted probability distribution. This makes the output less deterministic, but can sometimes lead to incoherent results if low probability words are chosen. Top sampling man. This method addresses that incoherence risk. It first limits the candidate pool to only the k most probable tokens, say the top 50, and then samples the next word only from within that smaller, high probability set. This prevents the model from choosing extremely unlikely, nonsensical words. Tops sampling, also called nucleus sampling. This is often preferred and is more dynamic. It selects the next token by sampling from the smallest set of tokens whose cumulative probability exceeds a predefined threshold, PAG 0.9. This cleverly prevents incoherent outputs from very low probability words, tail of the distribution, while still allowing for a flexible amount of diversity based on the context. If the model is very certain, the nucleus is small. If it's uncertain, the nucleus is larger, allowing more possibilities. Temperature scaling. This method directly adjusts the peakiness or flatness of the probability distribution using a parameter, often called BERT, or T. A low temperature, high bet, makes the distribution sharper, pushing the model towards more deterministic, high probability choices, closer to greedy. A high temperature, low bet, flattens the distribution, increasing randomness and diversity by making less probable words more likely to be chosen. Figure 5.6 in Foundations of LLMs beautifully illustrates how different temperatures affect the distribution shape. These sampling methods are absolutely crucial for creative tasks, giving LLMs their flair and unpredictability when needed.
Can we guide the model during decoding to actively avoid common pitfalls, like repeating itself constantly, or maybe to meet specific constraints we have for the output, like maintaining a certain tone or using specific keywords?
Yes, absolutely, through decoding with penalties. This involves adding penalty terms directly to the objective function that the decoding algorithm, like beam search or sampling, is trying to maximize. The formula conceptually looks like E equals argmax UIX, pre-XY, where penalty XY is a function that quantifies how much the generated sequence violates certain desired constraints and controls the strength of the penalty. Common types of penalties include a repetition penalty to discourage the model from generating the same words or phrases over and over again, a length penalty to encourage outputs to be closer to a desired length rather than being too short or rambling on too long, a diversity penalty to actively promote more varied vocabulary or sentence structures, often used in creative generation, and constraint-based penalties for specific content or style requirements, like ensuring a consistently positive tone, avoiding certain words, or ensuring specific terminology is used, for example, in technical writing. This allows for incorporating external knowledge, rules, or user-defined constraints directly into the generation process itself.
Okay, this next one sounds almost like magic. How can we drastically speed up decoding, particularly for very large models, without losing quality or introducing noticeable errors, given how inherently sequential it seems, word after word?
It's an ingenious technique called speculative decoding. This method uses a clever trick involving two models. It employs a draft model, which is typically a much smaller, faster, maybe less accurate LLM, to quickly predict several tokens ahead in one go. Then, a verification model. This is your full, larger, high-quality LLM checks these quickly predicted draft tokens in parallel using a single forward pass. If the draft model's predictions up to a certain point are correct, as verified by the larger model, they are all accepted in a batch, saving significant sequential computation time compared to the large model generating one token at a time. If an error is found at any point in the draft, the verification model takes over from that point, corrects the output, and then the process repeats. The immense benefit is that it can significantly speed up inference by effectively amortizing the computational cost of the verification model over multiple tokens whenever the draft is correct. Figure 5.7 in Foundations of LLMs illustrates how this process works, allowing you to generate text much faster, especially when the draft model is reasonably accurate.
Finally, the simple question. How does the LLM know when to stop talking? It can't just go on forever endlessly generating text, right?
Right. That's handled by stopping criteria, which are essential for practical, coherent LLM outputs. Most LLMs are explicitly trained during pre-training or fine-tuning to generate a special end-of-sequence token, often denoted as EOs or similar, to signal that they have completed their intended response. Beyond that specific token, common criteria used to halt generation include a predefined maximum output length to prevent overly verbose or potentially runaway responses, acting as a safety net, Time constraints for real-time applications like chatbots, ensuring a response is generated with an acceptable delay for the user experience, and various behavior-based criteria, such as stopping if the probability of the next predicted token drops below a certain confidence threshold, indicating the model is becoming unsure or less coherent, or if the model starts to detect excessive repetition of tokens or phrases, suggesting it might be stuck in a loop. These criteria work together to ensure that the generated text is both complete and reasonably concise.
Okay, inference speed and cost are absolutely huge factors in deploying AI in the real world. A slow or expensive LLM just isn't practical for many applications. How do engineers make LLM inference truly efficient? What are the key techniques for optimizing performance and minimizing cost?
The goals here are very clear for engineers. Primarily, reducing memory requirements and accelerating the system. This is a highly engineered aspect of LLM development, constantly pushing the boundaries of hardware capabilities and software optimization.
We mentioned the KV cache earlier as crucial for decoding efficiency, but also that it grows linearly with sequence length, which can eat up memory. How can we make that cache smarter to save precious GPU memory, especially for very long conversations or documents?
Right, the KV cache, which stores those past keys and values from attention layers to avoid recomputing them, is indeed critical for efficiency during decoding. However, its size can be enormous. It scales with OL, AEA, TH, AM, dependent on the number of transformer layers, L, the number of attention heads, the dimension of each head, DH, and most critically, the sequence length, M. For very long inputs or generations, this can quickly overwhelm even the most powerful GPU memory available. To optimize this, several clever techniques are used. Sliding window attention is one approach where the model only attends to, and therefore only needs to cache keys and values for, a fixed size window of recent tokens, say NoW. This reduces the cache memory complexity to OLEEDHMMW, making it independent of the total sequence length beyond that window. Similarly, a fixed size KV cache uses a constant memory model by literally only keeping a fixed size window of previous keys and values, regardless of the full sequence length, perhaps using strategies like CIFO, first in, first out. More advanced methods like compressive transformers employ two fixed-size memories, one for the immediate local context, like a sliding window, and another for storing a compressed summary of the long-term history, essentially summarizing what came much earlier without storing all the details. Some even use KNN-based memory, augmenting the standard attention mechanism with information retrieved from an external data store of past KV pairs seen during training or previous inference steps. This provides a kind of dynamic, retrievable long-term memory without infinite cache growth. These innovations are all about making better, smarter use of limited memory resources, which is often the key bottleneck.
Okay, that handles memory. What about throughput? Processing one user request at a time is incredibly inefficient for a server handling many users simultaneously. How do we manage many requests without slowing everything down to a crawl or wasting GPU cycles?
That's where batching and scheduling come in, which are critical for maximizing throughput requests processed per second. The core idea is simple. Batch multiple user requests together to fully utilize the parallel computing capabilities of GPUs. However, a major challenge, as we discussed, is that user requests often have highly variable sequence lengths. Some prompts are short, others are very long. If you just put them all in a static batch, the entire batch processing time is dictated by the longest sequence, leading to significant padding and wasted computation for the shorter sequences. The GPU sits idle waiting for the long one to finish. To address this inefficiency, several sophisticated strategies are employed. Dynamic batching adjusts the batch size on the fly based on incoming requests and available resources, trying to pack things efficiently. Bucketization groups requests of similar lengths into buckets, which are then batched together, significantly minimizing the amount of padding needed. You can see this visually in Figure 5.8c in Foundations of LLMs. A more advanced and widely adopted technique today is continuous batching, sometimes associated with systems like Orca or VLLM. This keeps the inference engine almost fully utilized by cleverly and dynamically interleaving the processing of prefilling and decoding steps for different sequences within the same iteration. It maximizes throughput by overlapping the compute-bound prefilling of new requests with the memory-bound decoding of ongoing requests.
And what about reducing latency, especially for users who submit very long prompts? A user doesn't want to wait minutes just for the prefilling phase of a long document summary request, for example.
Right. For long inputs, chunked prefilling is very effective at reducing that initial perceived latency. It divides a very long prefilling task into smaller, manageable chunks. This allows the decoding steps for other already prefilled sequences in the batch to start much sooner and overlap with the prefilling of the long sequence. This significantly reduces the time to first token latency for users and makes the system feel much more responsive even when handling long inputs. Figure 5.33 in the source illustrates how this chunking reduces idle time in the pipeline. These methods often fall under the umbrella of priority-based scheduling, allowing systems to dynamically prioritize certain requests or steps. For AG, prioritizing decoding steps for low latency in an interactive chatbot versus prioritizing prefilling for maximum overall throughput in a batch processing job, depending on the application's specific needs and SLAs.
Makes sense. Now, just like training, inference for the very largest models often needs parallelization to be practical and performant, right? How do those distributed training techniques we discussed earlier apply here, and are there unique challenges for inference compared to training?
Yes, many of the same parallelization techniques we discussed for training, data parallelism, model parallelism, tensor parallelism, and pipeline parallelism, are indeed also applied to inference, especially for models with hundreds of billions or trillions of parameters that simply won't fit or run fast enough on a single accelerator. However, applying them effectively to inference, especially in real-time user-facing scenarios, poses some unique challenges compared to offline training. Load imbalance due to highly variable length input sequences and, crucially, variable length generated outputs can be much more pronounced and harder to predict than in training. The constant communication overhead between devices can significantly impact end-to-end latency, which is often much more critical for inference than for training. And meeting strict real-time constraints adds another layer of complexity. As an example of architecture designed for efficient inference parallelization, mixture of experts, MoE models, are particularly interesting. And in MoE architecture, different experts, which are typically modular feed-forward networks within the transformer blocks, can be strategically assigned to different devices. During inference, for any given input token, only a small subset of these experts, maybe just one or two, are actually activated and executed based on a routing mechanism. This greatly improves efficiency because you're not activating the entire huge model for every single token computation. This allows for models with vastly more total parameters to be deployed much more efficiently than a dense model of equivalent size.
Okay, let's talk about this powerful concept again, inference time scaling. It's about making the model smarter during inference, not just faster or more efficient. What exactly is inference time scaling, and how does it push the boundaries of LLM capabilities at the moment of use?
Inference timescaling, as Foundations of LLMs explains, is the principle of incorporating more compute into inference, specifically to solve increasingly complex problems more effectively. This isn't about training a new model or doing more fine-tuning. It's about making the existing deployed model significantly more effective during its actual use by intelligently applying additional computational resources at that moment. It's a guiding principle for advanced systems like OpenAI's O1 and DeepSeek's R1, which demonstrate impressive performance on complex reasoning tasks by dynamically increasing computation at the time of inference based on the difficulty of the problem.
What are the different fascinating ways this inference time compute scaling can manifest in practice? How do you actually add more compute at inference?
There are four main categories emerging. First, context scaling, which we've touched on. This involves dynamically extending the input prompt provided to the LLM with helpful additional context right before generation. This includes techniques like providing more relevant few-shot examples, giving extensive chain of thought prompts that guide reasoning, or leveraging retrieval augmented generation, RAG, to inject external relevant information from knowledge bases or the web. More context often means more compute during the prefill stage. Second, search scaling, where you increase the computational effort during the decoding phase itself. This could mean generating much longer thinking paths or chain of thought sequences for complex math problems or code generation, essentially allowing the model more steps and time to reason. It can also involve scaling the search space, for example, by significantly increasing the beam width in beam search, or exploring sophisticated tree structures of reasoning steps, potentially using multiple LLM calls to evaluate different branches, as discussed by Yao et al. In 2024. Third, output ensembling, which we also touched on earlier in prompting. This involves generating multiple candidate outputs for the same query using sampling or diverse prompts, and then using additional computation, perhaps another model or a verification step, to combine them or select the best one, thereby mitigating individual model errors and improving overall robustness and exploration. And finally, a highly advanced and powerful category, generating and verifying thinking paths.
That last one sounds like it strongly connects back to our earlier discussions on chain of thought and self-refinement, and maybe even process supervision. How does inference time scaling enhance those ideas?
It absolutely does, yeah. For highly complex reasoning tasks like advanced mathematics, logical puzzles, or intricate code generation, LLMs often need to not just generate a sequence of reasoning steps, but also verify them and potentially self-correct along the way. This requires not just a search algorithm like beam search or sampling to explore possible solutions, but also a verifier. This verifier could be anything from a formal mathematical proof checker or a code compiler to a trained reward model, another LLM acting as a critic, or even simple heuristics like majority voting over multiple generated paths. Its job is to assess the quality and correctness of those intermediate reasoning steps or the final proposed solutions. This verification can be done in a parallel scaling approach. You generate k candidate solutions or reasoning paths independently using the LLM, then use the verifier to select the single best one, similar to best of n sampling but potentially verifying the entire path. This is shown in Figure 5.16 of Foundations of LLMs. Alternatively, you can use sequential scaling, where the LLM generates an initial solution or step, the verifier provides feedback, and then the LLM refines it iteratively based on that feedback. This is essentially the self-refinement process we talked about, but applied robustly and potentially multiple times at inference time. The most sophisticated approach is step-level search with verifiers, illustrated in Figure 5.17 of the source. Here, verification is integrated directly into the step-by-step generation of a reasoning path. After each potential step is generated, the verifier assesses it, allowing unpromising paths or incorrect steps to be pruned early on. This prevents wasted computation down wrong paths and leads to much more accurate and robust solutions for the most intricate problems by focusing compute on promising directions. This shows the remarkable ongoing innovation in making LLMs better reasoners at the point of use.
Okay, so after all this incredible engineering, the architectural work, the alignment efforts, the intricate optimization for inference, how do we actually know if our LLM's inference performance is good in a real-world context? How do we evaluate its performance effectively beyond just simple accuracy?
That's a great question. Beyond the foundational, often quantitative accuracy metrics like perplexity, which measures how well a probability model predicts a sample, lower is better, and task-specific scores like F1 score, which balances precision and recall for classification tasks, foundations of LLMs highlight several crucial evaluation dimensions that are much more user-centric and holistic. We need to assess robustness. How well does the LLM handle ambiguous inputs, noisy data, slightly out of distribution prompts, or even adversarial attacks without breaking down or giving nonsensical, unsafe answers? Usability is another absolutely key aspect. This measures the output's fluency, coherence, relevance to the prompt, and sometimes diversity, especially for creative tasks. This often relies heavily on human ratings or qualitative feedback, as it's hard to capture purely with automated metrics. Is the output actually useful and pleasant to interact with? And of course, ethical and fairness metrics are vital, especially given our earlier discussion on alignment. We need ways to measure and ensure the LLM avoids perpetuating harmful biases, gender, racial, etc., or generating toxic, unfair, or inappropriate content. Ultimately, choosing the right basket of evaluation metrics depends critically on the specific task and the intended application. There's often a significant trade-off between output quality, for example, accuracy, fluency, safety, and efficiency, for example, throughput, latency, cost. Finding the right balance and evaluating comprehensively across all these dimensions is a continuous challenge for engineers and researchers deploying these systems responsibly in the real world. It requires a comprehensive approach, something the AI Coach by Anil Nathu curriculum emphasizes for truly understanding an LLM's real-world value and impact.
Wow, what an incredible journey we've been on. From understanding the raw data and initial pre-training, through scaling and alignment, all the way to intelligent conversation and efficient execution at inference time. LLMs are truly complex, fascinating, and undeniably transformative systems. For you, our listener, who has followed along with this deep dive into the foundations of LLMs, what are the key, actionable takeaways? What should you really hold on to?
That's a great question. I think the core lessons are clear and provide an excellent roadmap for anyone interacting with or developing LLMs. First, understand the foundations. Really recognize that LLMs are built on that bedrock of pre-training, typically using self-supervised learning on massive, diverse data sets. This is the engine that gives them their vast general knowledge and, crucially, their incredible, often surprising, emergent abilities. Understanding this process explains why they can do so much. A strong foundation leads to broad capabilities. Second, master prompting. Remember, your interaction with an LLM is absolutely key to its performance. You need to employ good general prompt design principles, clarity, role, format. Leverage in-context learning by providing clear examples. And critically, for complex tasks, use techniques like chain of thought prompting to guide the LLM through the reasoning process. For specific, up-to-date, or factual knowledge, integrate RAG, retrieval augmented generation, and potentially tool use to ground the model and expand its capabilities beyond its internal knowledge. Third, prioritize alignment. Always be aware that LLMs must be actively aligned with human intentions and values to be safe, truthful, and genuinely helpful. Whether this alignment is achieved primarily through supervised fine-tuning, SFT, on specific instruction sets, or the more sophisticated process of reinforcement learning from human feedback, RLHF, understanding the need for alignment and how it's done is a crucial step for responsible AI deployment and effective use. Don't just assume a powerful model is inherently good or helpful. And finally, optimize for inference. For any practical, real-world application, efficient inference, the process of generating outputs, is vital. Consider techniques like smart batching and scheduling, effective caching, like KV caching optimizations, and perhaps even speculative decoding to maximize throughput and minimize latency. And keep an eye on the exciting developments in inference timescaling to enhance reasoning capabilities by providing more context or enabling verification during the model's actual operation. Efficiency matters hugely in practice.
Fantastic summary. And for you, our listener, here are some practical action steps you can try implementing right away, building directly on these key learnings. 1. Experiment with TOT. The very next time you're tackling a complex problem with an LM, maybe asking to solve a multi-step math problem, debug code, or plan something complex, try simply adding the phrase, "let's think step by step" to the end of your prompt. Just see what happens. Observe the difference in the LLM's reasoning process and the quality of its final output. 2. Test RAG in your own queries. Next time you need factual, current, or maybe domain-specific information from an LLM, instead of just asking the question directly, try providing relevant context like pasting in a snippet from a recent news article, a paragraph from a relevant document, or key data points directly in your prompt along with your question. See how it grounds the LLM's response and improves factual accuracy. 3. Reflect on alignment in your AI interactions. When you're designing how you interact with AI, or perhaps building AI-powered tools or features, take a moment to consider what ethical guidelines or human preferences your LLM should adhere to in that specific context. Even in simple prompts, think about how you might start to build those values into your instructions. For example, respond helpfully and politely, or by actively seeking out models known to be better aligned. 4. For developers, explore efficiency. If you're involved in deploying or building LLM systems, take some time to investigate how techniques like continuous batching, parameter-efficient fine-tuning, like LoRa or soft prompts, or even exploring speculative decoding could significantly optimize your LLM deployments for improved speed, reduced cost, and better user experience. This deep dive into LLM foundations provides you with actionable insights, and you can explore these concepts further and implement them using resources like those found at AI Coach by Anil Nathu. So we've seen how LLMs learn, how we guide them, how they reason, and how they execute their incredible capabilities. But here's a thought for you to ponder as we close. Given the accelerating power of scaling laws and the often unpredictable emergence of new abilities simply from increased scale and data, what new, as yet unseen capabilities might we unlock as these models continue to grow in size and sophistication? The future of AI might genuinely be less about what we explicitly program them to do, and more about what we intelligently enable them to discover for themselves. What lies beyond the next scaling threshold?
It's been a truly fascinating exploration, hasn't it? Delving into the intricate engineering and the profound design choices that shape the AI we interact with every single day, and that continues to redefine our technological landscape at such a rapid pace.
That wraps up our deep dive into the foundations of LLMs. We really hope you feel much more informed and ready to engage with this incredible technology. Thank you for joining us today. Visit the AI Coach website for more AI insights.